talk is on the non-uniform case-center problem given by Deeparnab Chakrabarty.
So thanks for letting me talk. So I'm going to talk about this new problem, the non-uniform case-center problem. It's a class, it's an example of an heterogeneous or non-uniform resource allocation or resource location problems, which this is one example, and they sort of change the complexity of well-known problems, and it's interesting to understand what kind of techniques will solve them. So this is the problem I want to talk about. So before I go into the non-uniform case-center problem, so what's the case-center problem? So this is a classic problem. So the input is a metric space and an integer k, and the objective is to find a subset of these points, k in size, so that this thing is minimized. So what is this thing? So for every point x in the metric space, I look at the minimum distance to the point in C. So this is dx comma c. And I look at the worst possible point. So I max over all points in x. This is the quantity that I want to minimize. So this is the original k-center problem. So in this picture, maybe k is 3. I want to put this red dot so that this is the max farthest point from this red dot, and this distance I want to minimize. Okay. So another way of putting this is the following. I am given k balls of radius 1, and I want to place these balls, I want to find the centers of these balls, so that with the minimum dilation alpha, these balls cover the whole metric space. Okay? So that's the same restating of this problem. Okay, so why is this problem interesting? Well, here's a very important application. I have a city, and I have ambulances, 3 ambulances maybe, and I want to figure out where to put these ambulances, depots for these ambulances, so that every house in the city, as close to these ambulances as possible. The ambulance can reach as soon as possible to the worst guy. Okay. So if you think I've made up this problem, I have, but so have other people. So this is one of the, if I started digging up the first paper which studied this case-center problem. It's a paper from the 70s, and it's sort of the motivation. Another interesting thing I found that this is a paper by Christofides, which is not on TSP. So there are lots of them. Okay, thought I'll put this out. Okay, so what's known about this problem? So this problem, if you think about it a bit, it's related to the dominating set problem. So in a graph, a dominating set is a set, so that every other node has at least one neighbor in that set. And finding the minimum dominating set is an NP-hard problem. And just this fact shows you that the k-center problem, you cannot get an approximation factor better than 2. Why? If you have a dominating set of size k, then the opt is 1. Everyone can connect to the center at hop 1. And if it is not k, then any k points you open, the minimum distance at least one guy has to travel is 2. Okay, so you cannot hope to get better than factor 2. This was noted in a paper by Sue and Hauser before I was born, and there was a very, very nice 2 approximation algorithm given after I was born. So, and I'll tell you what this 2 approximation is. This is by Dorit and David, and it's a beautiful algorithm. So here's the algorithm, right? So suppose opt is 1. I can scale the metric so that I can assume that the opt is 1, which means that there are k. I can put opt has you can put k balls so that it covers the whole metric space. So these are the opt balls. I don't know. So the algorithm says, take any point, draw a ball of radius 2, okay, and cover some points. Then take another point which is not not covered by these points, draw a ball of radius 2, and go on. So maybe you did 4, k is 4 here. And if I cover everything, I'm done. That's a 2 approximation because everyone is covered by balls of radius 2. And the claim is that you cover everyone because if there is another point which is not covered, there are k plus 1 points with pairwise distance at least 2. And by pigeonhole principle, one of these 2 must be in the same ball. But if they're in the same ball, they must be within distance 2. Okay, so it's a very, very, very nice algorithm which gives an optimal factor 2 approximation. So I'm just trying to say that how it's a very simple problem, very clever though. Okay. So coming back to this ambulance example, what if my ambulances had different rates, right? So I had two ambulances of which could move at 30 miles per hour, but one that could move at 60 miles per hour. Then the depot location problem of where should I put the ambulances changes, because the faster ambulance can cover a larger radius in the same amount of time, right? So this is sort of what I mean by the non-uniform case center problem. To solve this problem, I would like to have non-uniformity in my centers. And so let me make the problem concrete. Okay. So I must say that these slides were made painstakingly last night. So you'll see some weird animation here and there. Okay. Here's the problem. So I've given a metric space x comma d, and now instead of one number k, I'm given k1 r1, k2 r2 up to kh rh. Okay. So these r's are like the rates of the ambulances. What's the objective? The objective are to put centers. So there are k1 centers of radius r1, kh centers of radius rh. So I have to put the centers. And again, I want to, for every client, it looks at the nearest center it can get to divided by the rate of that center. Okay. So it's dx comma c by rc if the center of type C is opened there. And I want to again look at the worst client, the client who gets served the latest. Okay. So let me. I think this is clearer if I put the sort of the ball notation. So again, so again I have endpoints in the metric space, and now I have balls, k1 balls of radius r1, k2 balls of radius r2, kh balls of radius rh. Instead of like k balls of radius 1, I have now different classes of balls. And I want to find the centers of these balls. So some balls are large, some balls are small, so that this minimum dilation of these balls covers the whole metric space. Okay? That's the problem. So is the problem clear? Any questions? Yeah.
Why are you bunching the distances together?
Good. I could have just said R1, there could have been repetitions here, right? As in, that's what you mean? Like, yeah, so this will play a role. So how many types of rates I have will play a role. So in the case center problem, I had only one radius, all of one. And this, the whole point of this talk is to get people excited to solve the problem depending on the complexity of H. So you'll, yeah, there's the reason I'm doing this. So this is going to be a short talk, so please ask questions, otherwise I'll finish early and demolish and take my time. Yeah. So having said that. Okay, so here's the reason, one reason you might be excited, that this problem actually generalizes another problem, which is the case centers with outliers problem. So which is, what is this problem? So again, in a metric space, I'm given two integers, k and z, and the objective is to, cover all, but maybe z points I don't need to cover, right? So if I, what is the, again, the objective is the same. I want to minimize the worst client's distance served, right? So I claim that this is a special case of the non-uniform case center problem with two kinds of radius, where the radius are, I have k balls of radius 1, and I have z balls of radius 0. So I'll just put the z balls on the outliers, and the other k balls will expand the same rate. Okay, so this problem does, it generalizes another problem. So when you generalize two problems, I think it makes it worthy of study. So what's known about this problem? So if you think about it, this algorithm, you might say, well, let me keep growing these balls till z people are left out. And that sort of doesn't work. And you have to be a little more clever. And there's a greedy algorithm, so you have to grow these balls in a greedy fashion. And this was given by a paper by Moses, Samir Kuller, Narsimhan, and Mount, SOTA 2001. And there was a 3 approximation. So you lose a factor, the 2 becomes a 3. But it's a very clever algorithm, combinatorial. Okay? So that was known for this problem. Okay. So what do we get? What are the results that we have? So when there are only two kinds of radius, right? So there are K1 of radius R1, K2 of radius R2, we can get a constant factor approximation. Constant is not that bad, it's 1 plus square root 5 and probably can be brought down. And in particular, for the outlier version where one of the radius is 0, we can get a 2-factor approximation. And it's pretty simple. That's one kind of result. And we have what I call a brittle impossibility of unicriteria algorithms. So if the number of types of radius is part of input, you cannot hope to get unicriteria algorithms. No factor basically. Okay? And I will say what I mean by brittle here. Okay? So when you have an impossibility of unicriteria result, you'd like to see if you can do anything bicriteria. What does bicriteria mean? Can you open more centers with this and get an algorithm? And that we can. So we can get an order 1 bicriteria approximation, which means that I can open order ki centers of type I, and each of them will also violate the balls of radius order Ri. Okay? So there will be constant. I'm not going to talk about this. This is sort of takes more work, but I'm going to show order log star n order 1. But I think the main sort of surprise for me was that this problem is connected to another problem called the so-called Firefighter problem. In fact, the Firefighter problem on trees. And maybe I'll remind you of that problem, or if you've heard it for the first time, this is a very cool problem. I'm given a tree, and let me not go into the story, but here's the problem. Here's the thing that we need to find. We need to select a bunch of nodes n, such that every root leaf path has one node from n. Okay? And the constraint is that every layer, so the rooted tree can be thought of as a layer graph, every layer should have at most b nodes. And I want to minimize b. That's the Firefighter problem. Is the problem clear? So the first time you think about it, if you have not heard of it, it seems like this problem should be easy to solve. But what is quite amazing is that it is NP hard to decide between b equal to 1 and b equal to 2. So even when the tree has a lot of structure. This problem is it's NP hard to decide whether I can have 1 per layer and save all the leaves, or 2 per layer and save all the leaves. See some puzzle faces. Is this clear? Okay.
But you can't do anything in the leaves. You don't want to touch the leaves.
You can touch the leaf. You can touch at most 1 leaf, say. Yeah, B leaves. Yeah. It doesn't change the problem. On the other hand, if you think about it, that this problem, if the tree is of small depth, then there's a polynomial time algorithm via dynamic program. Okay, so there's a reason I'm telling that. So small depth trees are solvable. So this is a connection to NUKC. So suppose I have the hard instance for Firefighter, and I want to construct a metric. So here's the metric. Basically, it's the tree metric where the costs are exponentially growing. So on these I just have cost c. These have c square all the way up to c to the h. C is I'm trying to say that there is no c factor algorithm. So that's the metric. And what do I have as the radii? So I have 1 ball of radius ch, 1 ball of radius c to the h minus 1 ball of radius c. Right? And now you can see that, sort of convince yourself that if there was a way to put 1 node at each level to make all the leaves survive, you'll basically put a ball of that radius in that place in the metric space and save all the subtree leaves. So if the Firefighter value is 1, if 1 leaf suffices, then I can have basically every client will travel at most 2, and when by travel I mean travel divided by the rate. On the other hand, if you cannot put 1 guy at every layer and save all the leaves, then no matter what you do in this NUKC instance, someone has to travel a subtree straddle a subtree and will basically pay C. Okay, so this is sort of standard. So you cannot get better than C by 2 factor. Okay. So but note that this is brittle. So why is it brittle? First of all, the diameter. So suppose I want to say there is no. Actually, if the number of types that is H, and H was a constant, then the hardness just breaks down because the firefighter problem is easy on it. And in fact, the NP hardness kicks in only when the number of types is like theta n. So here's an open problem, and this is you can. I remember giving a talk once, and I gave an open problem in the middle, and Michel said that he started working on and didn't listen to the rest of my talk. But the problem is that solve this problem, get unicriteria algorithms for constant H, even 3. Okay, so having said that, let me move on to the algorithmic part. So we showed that the firefighter problem leads to hardness for this NUKC problem, non-uniform case-centered problem. And I would like to say that the firefighter algorithms lead to algorithms for this problem. Okay, and the way that will go is via LP relaxation. So we're going to write a natural LP relaxation for the non-uniform case-centered problem, and then we'll convert it into we'll get a tree and a feasible solution to a natural LP relaxation to the firefighter problem, which has all the properties you need. So here's the LP. So let me write this LP there so that. So it says it's a standard LP. It says so there's a variable xqt which says to what extent a ball of radius type t is opened at the point q, right? Xqt. So variable xqt, and what do I want? So I'm going to assume that I can cover the whole metric space with no dilation. Now, optimal dilation 1. This is without loss of generality. So if this is the case, then the LP must say the following. So for every point P in X, there must be a ball that covers it. That ball could be of one of this H types of radius, T equal to 1 to H. And indeed, if it is covered by a ball of radius RT, there must be a point Q within distance RT where you have opened a ball of that radius. So let me write that. Let me write it slightly differently. So Q such that distance of P to Q is at most RT, XQT, and this should be at least 1. Clear? So this is just a normal covering constraint. So that's one constraint. And the second type of constraint says that, well, you cannot open too many balls of the same type. So for every type T, you look at how many balls you've opened of that type, that's just the sum, that should be at most KT. Standard LP. Any questions? Okay. Yeah, this is not hard. Okay, so I solve this LP, and now we do the following. I'm going to construct a tree and a fractional values on those trees. So the leaves of the tree are my points on the metric space, and the fractional value y on this is 0. So this is the picture, and my radii are, I'm assuming, are R1 bigger than R2 up to bigger than RH. Okay. So at level I, so I have grown this tree up to this level I, and what happens is there is going to be one winner who trickles up. So these points are going to trickle up. One of them will trickle up as a winner. So for example, in this two, among these two, one of them is a winner. The winner goes up. Here, the pink one goes up is a winner. Yellow up goes up as a winner. Okay, so the winners are trickling up. I'll tell you who are the winners. Again, so this is a node in the tree, but all nodes correspond to certain points in the metric space, just by figuring out who is there in the leaf. And the y value at the winners is what? So at level I, yu, which basically corresponds to a point P, is the coverage that P gets by radius radius of type I. Okay, so YU is, I look at all points within distance Ri and how much amount of coverage is by balls of radius I. Okay, so that's YU. So that's how the Y mass is given on each node. Okay. Clear? Good. So I have to tell you how this trickling up happens.
So Deepak,
Yeah.
the I is, so these are the, each level corresponds to one type.
Good. So each level corresponds to one of these 1 to H. Yeah, and H starts here and H goes up. Okay, good. So who do I propagate up? So there's a greedy rule here, and this is the only probably one non-triviality in this algorithm, that I cannot just propagate anyone. I propagate the guy who has more. So these levels are capturing how much coverage are by balls of radius I and below, and I propagate the guy I who has the least coverage from those radius I and below. Okay, so let me make it concrete. So for any point P, so I know that if I sum from 1 to H, this thing is at least 1, and this is summing up from I to H. So this is the coverage that point P gets from balls of radius I and smaller, Ri plus 1 in this. So among these points, whoever has the smallest coverage is the one who propagates up. Okay. So for example, in this picture, maybe these are the coverages from below. So the guy which has the smallest coverage below, the red guy, will be the winner. Okay. So let me describe the algorithm. So he's going to be the winner. And now this red guy in the metric space draws a ball of radius 2 Ri minus 1, similar to this idea. So draws a ball of 2 Ri minus 1, and whichever winners of the level I it sees, maybe it sees this yellow guy, that guy becomes its child. With a bunch of winners, I look at the coverage below this level. I look at the guy with the minimum coverage. That guy transcends up, draws a ball of radius 2 Ri minus 1, the radius for the level I minus 1. It sees some, probably, if it sees no one, it has no neighbors. But say it sees this yellow guy in that ball of radius 2 Ri minus 1 in the metric space. That's his new children. Okay? And then the whole tree is finished. So then I look at the remaining guys in this level. Whoever has the smallest coverage value, that fellow trickles up. Okay? And this goes on. Okay, so there are two things I need to show. And one thing I again need to show. So what happens when I do this balls of radius 2 Ri minus 1? What happens is, if I look at the total Y mass on any level, that will be equal to basically this mass, right? Because any 2 points, so for example, the red guy and the blue guy, the total Y mass that I put them, because they're balls of radius 2 Ri, they cannot share points. So these points which are within radius Ri are disjoint for the red guy and the blue guy. And therefore, if I sum the Yi's, it's as if I'm summing the XQI's, and there is no double counting. So the total mass, the Y mass on each level, is at most Ki. Okay, so that's going to be one thing that's going to be important. And the fact that I'm propagating up in this greedy fashion is that when I end, every root leaf path will have at least value 1, Y value 1, sum of Y value 1. Why? So for example, in this picture, the red guy won all the way. And the red guy has total Y value 1 because it was just the XQT that it faced it. So it was a coverage at level H, H minus 1, and so on up to this root. And therefore, that guy is 1. And then, but I'm going to claim that means that the yellow guy is 1, because whenever the yellow guy gave power to the red guy, its coverage below is only larger. Okay? So all in all, this construction gives this tree and a Y value on the nodes, such that 2 things. One, every root leaf path has total Y value 1, and every layer has total, layer I has total Y value at least Ki. That's like Sorry?
At most.
At most ki. But that's a fractional firefighter. So I'm putting fractional firefighters. Fractionally, I'm putting these nodes on this tree so that every root leaf path is covered and every layer has at most. So it's a non-uniform version, but that's fine. Every layer I has at most ki firefighter. So that was what we wanted to do, get from an LP solution for the non-uniform case center to this firefighter. And why did you want to do? Because so maybe this is the lemma that we get. If the firefighter LP for height h trees has integrality gap rho h, then we can open rho h KT balls. That will be the violation when the number of firefighters are opened up. And this is I did not do this, but the total coverage, every client can connect to one of these centers by traveling this much, which is the sum of the radius which it needs to travel. Okay, so that's a lemma. And then if you do standard tricks by saying that just club radii is at powers of 2. Oh, okay. So before I do standard tricks, what is this rho h? So it turns out that for height 2 trees, this is a trivial actually observation, the firefighter LP has no gap. So for when 2 radii, this implies a constant factor. And in fact, when one of them is R1 is 1 and R2 is 0, you get 2 factor. So that's a 2 factor for the case center with outliers. This breaks down at 3 type of radii because I think firefighter problem, the integrality gap is not 1 even when for height 3 trees. Definitely not for height 4 trees, but maybe not for even height 3 trees. So it breaks down very soon. So this approach won't work for the problem that I said. And again, in general, for any tree, the integrality gap is log star n. And if you do the standard tricks of grouping this radius in powers of 2, you'll get a log star n 8 approximation. Okay. So this is this log star n result is a very nice result by Chalam, Suk and Chuzoy, 2010. And I sort of, if you remember, I promised an order 1. So how is and this LP integrality gap is actually tight. You cannot be better than log star n. But I promised an order 1. And this actually came up because of a fantastic result by Rico, who's in the audience, and Ajiashvili and Baggio from Soda 16 or 17?
17.
Soda 17, but it was found in 2016, as always happens. And they gave an order 1 approximation for the firefighter problem. And it's not a black box thing, but if you go into their technique, and I think Rico should give a 1-hour talk, and then I can follow up on this. You can get an order 1 approximation. Okay, so you need to do a little more work to get an order 1 approximation. Okay, so again, I'm going to restate my open problem. Is that when h is constant, when h is 3, can you get constant factors? And in general, if you think about as a generalization of case center with outliers, if you think about it as a nuanced clustering problem, I have big clusters, medium clusters, small clusters. Can you solve these clustering problems? So we don't know, and that's very curious. As in, this LP integrality gap is bad, so how do you attack this problem? Okay, so this is what we saw. We saw a non-homogeneous, it's a non-trivial generalization. Open algorithm for constantly many types, connection to the firefighter problem. But when you look at these resource allocation problems with different kinds of resources, similar thing happens. For example, we again looked at the capacitated case center problem. So we have this heterogeneous capacitated case center problem in IPCO this year. Again, if you have constantly many capacities, it's open to get unique. So there are no unique criteria algorithms in general, but if you have constantly many types, I don't know if you can get unique criteria order 1 approximations. And here there was connection to some scheduling problems which are still open. So with that, I will.
Questions?
So I think you said this, but I'm just not sure I caught it. Outliers in 2. Do you know anything for that? So 3 h equals 3, but one of them is 0.
See, I'm actually not 100% sure if h equal to 3 is we cannot do because I'm not sure if integrality gap comes in already, but there are experts here. Where's Parinya? There are experts here who said that they can. So, but if there is an integrality gap, this technique won't work. Some other techniques might. But yeah, to answer your question, I don't know. That's a small answer.
What's cardinality constrained scheduling?
Yeah. So here, okay, here's a problem. I do just look normal make span minimization, identical machines. So there isn't p-task for that. But now I just say every machine can get at most fi jobs, and there's no p-task for that yet.
Yeah, the extent we know we have in general is a bi-criteria, but is it reasonable to hope for a unit criteria in the opposite way, where you're only losing in the number of centers but not the radius?
You can't do that even for the regular case center with set cover.
Yeah, exactly. As in maybe log n if you allow.
Okay, so log n is the best you can hope for. Now.
Yeah, even for the one center.
Can you get log n or not?
For these multiple things,
Yeah.
possibly it's a covering problem.
It's just also a set cover problem. You're covering. Yeah. Yeah. You can get
I
it.
think so, yeah.
So can you do the median thing?
Sorry. Yeah. Another obvious problem, can you ask for, we did for K center, can you do for K median, K means? Because K median with outliers, there is a constant factor, but it's pretty complicated as far as I know, unlike the K center with outliers. We cannot. This technique fails, and the point where it fails, you can exactly do the same thing, but so there's a greedy rule in trickling up this thing, and in K median, there's already another way to look at clients by their connection costs, and these two they can be different. And that's a technical reason why this doesn't work. So yeah, it does not. We don't know for median what to do. For median for two types even, we don't know if there are constant. So the hardnesses all go through. Median is hard, and even on a line it's hard. So, but if you look at constantly many types, in fact 2 types, we could not make this go through. Yeah, that's a good point. I should have.
Okay, thank you very much.
Thanks.